These are the notes for the second law of motion, which is LT4. One of your goals here is to be able to solve problems, so calculations involving force, mass, and acceleration for straight line motion, so for objects in linear motion. It'll be important to add these formulas. When I say add, these aren't new formulas, but to rearrange this formula on your formula sheet if you struggle with how to solve equations. So if just by looking at this formula you could not solve for acceleration or mass, you need to rearrange, then write this on your formula sheet. It is not cheating. You may use it on unit tests or at the learning targets, at the stations for learning targets. So pause me if you need to, but don't blow this part off. Make sure you actually get that on there. All right, so first thing we're going to do is talk about what is the second law in terms of just like a Google definition. And the law says that acceleration, which is A, depends on the mass of the object and the amount of force applied. All right. So hopefully we know, all right, we got acceleration is A, that the m is the mass, and then the F is the force. Okay, we probably already know that. All right, so a couple relationships, and we've worked on this in class already, but think about what happens with force and within a problem, and how that would affect the acceleration. And one of the most important relationships that you need to understand is that a larger force causes a greater acceleration. And for the most part, this is common sense. We know if we bunt at a softball, so apply a little force to something, versus home run swing, hit that thing, you're going to get a bigger change in motion, a bigger acceleration. Just barely touch a kickball versus wallop that thing, right? You have a bigger change in motion. We say that these are directly proportional. So two things are directly proportional when each variable responds in the same way. So if we pick on my dog again, if I feed Lily too much food, okay, so I feed her lots of food, then her body weight goes up. We're just calling it BW. You don't even need to write that part down. Not important, just giving you an example here. So more food, up goes Lily's body weight. We could say less food, down goes her body weight. They go the same direction. All right, so that's what I mean by this idea of directly proportional. So if you apply a little force, you get less of a change in motion. We contrast that to the relationship between mass and acceleration. A more massive object makes it harder to change its motion. That might be the best way of saying it. So if you have an elephant sitting in your seat when you come into class, good luck. Right? Try pushing that elephant out of your chair versus a cute little cat is sitting in your seat. Well, pick that cat up, right? Less mass means it's easier to accelerate. This relationship is inversely proportional. Okay, so that means they have an inverse relationship. Think of it as opposite. They're oppositely related. So maybe it could be like if we throw my poor dog back under the bus here. Let's say if we walk my dog more, so she gets more walking, maybe we see that she has less body weight. All right, so you do more of one, the other side goes down. Maybe we say that, for me, for sure, if I get less sleep here, I am more cranky. Yes, imagine that. I get a lot of sleep, so you don't want to see that day, all right? So less sleep, more cranky. See how those go in opposite ways. All right, so that's the conceptual part. Another part that we need to understand is that acceleration, which is A, is always, so no exceptions to this, in the same direction as the net force. Okay, it's always in the same direction as the net force. One of the things that people like to do to us teachers at assemblies is put us up against the varsity football team. Okay, especially homecoming assemblies, mock Olympics, that sort of thing. Now, I've exaggerated this, but here's your scrawny teachers, and here's the brutes. Here's the big old football players. I would hope, it's a sad day, when the teachers could beat the varsity football team. So if we're playing a game of tug of war, that's the rope. You know how my drawings go. There's the rope. I hope that the varsity football team can place a bigger force on the rope than the teachers. Therefore, the net force would be directed towards the football players, and therefore they are going to drag our scrawny butts towards them. Okay, so we would accelerate in the same direction as the net force. Okay, there will never be any exceptions to that. If two people are arm wrestling, whoever has the ability to put the net force, a bigger net force, on the other person, the hands go in that direction. All right, so that's the next part. Now, all that's really left are the calculations. And so I'm going to let you see this sheet. Hopefully you have it. There's examples on Moodle too. But I'm just going to put a couple of these. And what you should do, actually, I'm going to write it on here. You should put these in your notes so when it gets final exam time, you have them here. So maybe pause me and transfer them onto here once we go through it. We're going to start with an easier one. We're going to start with 2. We're going to skip 1 and 5. Those are a little trickier. But it says calculate the resulting acceleration. So A is what we want. So like in math class, that would be our X. Of placing a 12 Newton force, so there's our F, on a 3.5 kilogram object. We have to know our units. Kilograms is the unit for mass. All right, and of course, round to the nearest tenth for Moodle. So as I mentioned right at the beginning here, you should have these formulas added, tweaked on your formula sheet. And accelerations, what we're looking for is force divided by mass. So A is F divided by M, which is 12 newtons divided by 3.5 kilograms. And if we type that into the calculator, it's going to be 12 divided by 3.5. And we get 3.42. Remember to round, we need that 4. And that 2 says, since it's 5 and under, we keep the 4. We don't drop it to, or I'm sorry, we don't round it up. We leave it as it is. So 3.4. The units are technically meters per second squared, but in Moodle, we just type in 3.4. For mass, I'm not going to do number 3, but it's right here. You would just take the force divided by the acceleration. So here's the acceleration, here's the force. Okay, so the mass would be 100 divided by 11. You can type that in, see what you would get. For number 4, same idea, except now we want force. So it's mass multiplied by acceleration. So you're just going to take the 15,000, multiply it by 0.95. I better put them in parentheses. Okay, so you multiply those together and get a relatively big number. All right. So these ones are pretty straightforward. You just need to talk to me in class if any of those lose you. It's 1 and 5 that are logic problems, you could say. And it says, if the acceleration of a sled is 10 meters per second every second. All right, so 10 is the most important thing out of that. And both the applied force and the mass are doubled. What's the new acceleration? The way I like to do these is to write down that original acceleration so that I can think it through. And then handle net force and mass separately. Okay, don't try to do it all together in your head. Let's say the net force is doubled first. So you are pulling somebody in a wagon and you would all of a sudden pull twice as hard. I think good logic says if you pull twice as hard, we're going to accelerate twice as much. So 10 multiplied by 2 is 20. So this is gone now. We've dealt with it. We've dealt with our net force. The mass though, so you're accelerating something at 20 and all of a sudden maybe you're pulling one kid in a wagon and the neighbor kid jumps in, all right? And that neighbor kid happens to double the mass of the wagon. Well, holy smokes, if you don't pull any harder, then you're going to slow down. So we would need to divide that acceleration then by 2. We're going to be going slower, right? We're going to change our motion in a negative direction. So 20 divided by 2 takes us right back to 10. So 10 is your final answer for that one. And it goes back to this. If you increase force, you've got to increase your acceleration at that rate. Decrease, force, you decrease your acceleration at that rate. For mass, if you have more of a mass, you're going to get less acceleration. You have less in that wagon, then you would end up speeding up. Your motion would be in a positive direction. You'd go faster. Let's look at number 5. Acceleration of a sled is 18 meters per second. Write down the 18. Net force is doubled. Mass is cut in half. Handle them separately. Net force is doubled. Net force goes up. Acceleration goes up at the same rate. We're at 36. Gone. But now the mass is cut in half. Biggest mistake when people see this, they see cut in half and they automatically divide by 2. Just stop and use some common sense again. If you're pulling on a wagon or a sled and it all of a sudden gets lighter, you're going to go faster. We should have a bigger number here. So instead of, if this is our half here, instead of dividing by 2, we would want to get twice the size. So you're going to multiply it because we're going to be going faster. And so your answer for this one is 72. Okay. There are more practice problems on Moodle. I would highly suggest you go through them to make sure that you can answer those. And just scroll in Moodle once you click on it because the answer key should be in there. All right, good luck.